Hi engineering students, welcome to week 5, second video. I want to start with some quick little warm-up activities as I look through your homework. The stuff you turn in, I think one of the most consistent things I'm seeing that messes people up is just simply knowing which direction I and J are in two-dimensional problems, positive and negative, just getting that sorted out. I'm seeing good numbers, but incorrect directions and things. So let me give you some to quickly test you. Let's say that you had a force that looked just like that. I want you to tell me, say it out loud if you can. How would you write this with I and J notation? Okay, the correct answer would be, according to the way I've been showing you, 2I plus 3J, and then if it's a force, you got to put the units, newtons or pounds. Okay, you show the I, then the J, and then the unit at the end. We're not using matrix notation here, although it's cool if you want to try that. We're not using commas or anything like that. You actually show the positive and negative for both. It's like one line equation. And remember what this is doing. This is saying that we have a positive I direction and a positive J direction. Okay, the I is horizontal and the J is vertical. So that 2 refers to this distance right here. The 3 refers to this distance right here. Okay, that is where that is coming from. Notice that in the same way that the original black vector is to the right and up, just so the green vector is to the right, the red arrow is up. Okay, it always is going to match up like that. Here's another one. What would you do if that was a force vector? See if you can say it out loud. What you should have is negative 4I plus 2J. Again, if it's a force vector, newtons or pounds, if we're in US customary. And this is because it's a negative 4, because this is running counter to our traditional positive direction of I, which is the same as XY axes. And the positive 2 here is because you went up and not down vertically. Let me give you one more of these. Excuse my drawing there. And my coughing. Okay, that was plenty of time for you to work that out. So what you should have is negative 2I minus 3J. And again, put your units. And this is because you went across to the left and then down. Okay. So again, I'm seeing correct numbers, but weird directions, like people making everything positive or getting the I's and the J's messed up. And please always do write the I, then the J. This example on the screen, this is a great little one to just keep in front of you if you ever need a good solid reminder. Okay, now a quick little recap of what we did in the first video this week, because I believe that recaps are tremendously important. This is a table. I use furniture a lot as examples because firstly I want you to think about furniture, and also furniture is typically a statics problem. We don't want furniture to be moving, so we are generally dealing with the fact that sum of all forces equals 0. Now this table has a weight of 80 pounds, okay, a weight force of 80 pounds. And I am also pushing to the side, okay, I'm like leaning against it, and I'm doing 10 pounds of force to the side. So if this is true, that sigma F equals 0, then I want you to tell me what is missing from this diagram that we looked at just a couple of days ago. So firstly, vertically. The table is not accelerating downwards through the floor. So there is a ground contact force, okay, or an external contact force, or however we want to phrase that exactly. And because we know, oops, apologies, because we know that everything balances out to zero, we know that these two forces on the two leftmost legs, there must be 40 pounds. On the two rightmost legs, there must be another 40 pounds, so that it perfectly equals that 80. Now, horizontally, there must be some kind of friction force. We also looked at this just a couple days ago. If I'm pushing with 10 pounds sideways, but the thing is not accelerating, it's not sliding across the floor, then the only explanation is that there is 5 pounds of force there and there. Okay, because then it will all equal out to be 0 horizontally, 0 vertically. Okay, I won't even get into the Coulomb friction rule of F equals mu n, but we're just saying because we know this is a statics situation, those other forces may be filled in. We can know them with certainty. All right, let's also recap something else here. We talked last time about a philosophy or a theology of engineering. And we mentioned three big things here. We said that in the first chapter of Genesis, God gave all of humankind something that we often see called the creation mandate. Okay, Genesis chapter 1. Be fruitful, multiply, fill the earth, subdue it, spread out, take over, that kind of thing, in a stewardship kind of way, not in a domineering dictator kind of way. We also know that in the Old Testament, and then reiterated by Christ, are what we call the greatest commandments. These are the ones that say, love the Lord your God with all your heart, soul, mind, and strength, and your neighbor as yourself. Those were both in the Old Testament. I didn't really say that last time. I mentioned that the first one was in Deuteronomy. The other one was actually in Leviticus. So they were always there, but Christ pulled those out and said, these are the most important. And they come as a set. Can't do one without the other. And then the third one is the Great Commission. This is a more specific command given to Jesus' disciples, to his church, not to all creation, but just to his church, to go and make disciples of all the nations, okay, teaching them, baptizing them, getting them ready. Now, none of these three we said, cancel out any of the others. They all still stand. They're all very important. And they really do create a very helpful framework to know what it is that we should be about with our lives. And so today I want to give you three examples of people in history who really did this quite well. And they all happen to be men, and they all happen to be American. Let me start with these guys. These are the Wright Brothers, which I believe you would have known already. I'm reading a really good biography right now called The Wright Brothers by David McCullough. And the Wright brothers were sons of a bishop. Okay, so they were absolutely believers. They were brought up to know the Bible and literature and history. The bishop was quite well read for someone in Dayton, Ohio, in a time when literature and history were not necessarily very widespread with public education. They are often pictured as kind of lucky, persistent bicycle mechanics, and that's they just kind of worked it out by sheer pluck. Well, they were maybe a little lucky. They were persistent. They did have a bicycle shop, and they did quite well. They designed bicycles, like new designs. There was a huge bicycle craze. Everyone was going nuts over bicycles at this point in history, and they capitalized on that. But they also were real scientists and engineers. They gathered the flight test data from some other men who were doing similar work over in Europe, Octave Chanute in France and Otto Lilienthal in Germany, I believe. And so they actually had like measurements of like wing camber. Those who did the class last year in the 11th, 12th grade, know about camber and chord length and all those kind of things. So they were tracking that kind of stuff. They built their own wind tunnel. They were testing different shapes. They really were going about it in a very scientific fashion. So these guys really epitomized this kind of stuff that we're talking about. And I would describe it as saying they subdued the wind, like part of creation. They had mastery over the wind. That was one of their goals. Looking at the birds, seeing how the birds master the wind, they wanted to do the same thing. They had a solid reputation as men for loving and respecting those around them, like living by biblical standards. And then by the invention that they made useful, people were enabled to spread more rapidly around the world, like as in exercise the creation mandate. In the red corner, aircraft have often been used to spread the gospel directly. They've, for example, dropped flyers over communist China, and people, get these flyers. They're not allowed to follow Christianity. They get them, and there's like, Bible quotes printed, and they literally give their lives to the Lord in rebellion against the communist government there. You got missionaries reaching out into the tribe in Ecuador that was made very popular in a movie recently, The End of the Spear, I think it was called. And that was the beginnings of the organization Mission Aviation Fellowship, who I worked with. So the aircraft is very directly related to all these things that we've talked about. Going a little more kind of science style here, but not absolutely engineering technology. This guy's not quite as well known. His name is Raymond Damadian, if I'm saying that correctly. I'm not sure if I am. He's still alive. He's a physician, and he invented the MRI scanner. And he he also became a Christian. He was 21 and went to a Billy Graham crusade. It's where they pack out a huge stadium, and they have the music and have the message, and many thousands of people came to know the Lord through those activities. But even before his age 21 conversion, he was really fascinated by the problem of what's going on inside the human body, particularly as regards cancer and illness, because his grandmother died of cancer when he was 10. So he had this splinter in his mind that he just couldn't shake, and he wanted to know more about it. So his invention is absolutely able to fulfill these things that we talked about. He is able to, as it were, subdue and understand the human body, part of creation. By his invention, we have a much greater understanding of people's sicknesses and how they can be made well, and in a very unobtrusive way, by the way. His invention is not an X-ray machine. It is not. It doesn't involve any kind of radiation. It actually uses magnetic fields, and then the particular atoms and molecules and things in the human body behave in a particular way in the presence of that magnetic field, then that is measured and made into an image. So that's how it works. It's kind of almost like a passive system, if you like, as opposed to an active radiation system like an X-ray. So this is a very real, very effective way of loving other people. And our last example today, as I said, all Americans as it happens. This is George Washington Carver. Okay, that's his last name, George Washington Carver. And you might have heard of him as the inventor of peanut butter. From what I could read, I don't believe that is actually true, but he did have a lot to do with peanut crops. He published like a lot of articles and things trying to popularize peanuts because he was leading major agricultural initiatives in all sorts of different crops in the late 1800s and early 1900s. He died right in the middle of World War II, by the way. So he was actually born as a slave, born into a slave family, just a few years before the Civil War happened, before emancipation. So started life as a slave, and then, in his upbringing, he was right there in the middle of what we call the Reconstruction era. Okay, where the country was attempted to be, put back together, as it were, North and South, slave and free. What do you do with all the recently freed slaves? How do they live? How do they find work that is not slavery? A lot of problems. And so he actually George Washington Carver worked as a professor at the famous Tuskegee Institute, which was led by Booker T. Washington. And it was specifically aimed at former slaves and giving them solid skills in agriculture, in construction, in all sorts of fields, very practical skills, so they could work and support their own families and have dignity. So George Washington Carver's work was huge. He used his science and technology leadership to promote flourishing, to improve the lives of others across the whole nation. And he showed people how to have mastery over the soil, how to understand it, how to work with it, and how to really improve it. Because if you can improve the quality of food and farming, then you really directly, at a very base level, improve the lives of people. Okay, food, quality of life, directly related to farming, always has been. He, by the way, was also a believer. He was converted at age 10, and he saw his faith as being directly undergirding both his scientific, technical engineering style work, but also as he directly promoted racial harmony in those turbulent, difficult years of Reconstruction. His faith was strong and constantly motivating him. Okay. Let's jump now into the mathematics of today. We are going to try to look for some white space. Here we go. We'll do it right here. We're going to talk about springs. It was there in the book, and I am going to actually make a little bit of a departure from the notation that the book uses. The book uses a delta notation. Book says F equals K delta X. Now this, if you're wondering, just off to the side here, this is the lowercase delta. Okay, it's the lowercase d in the Greek alphabet, whereas the one that I was using the other day was the uppercase d in the Greek alphabet. And then he's also doing like d subscript x, like it's a delta x, okay? Change in distance is what he means. I personally actually favor a slightly simpler notation in this case, just F equals kx. So I'm gonna talk in terms of that, but I'm describing exactly the same phenomenon that the author is, okay? I just think that delta x is unnecessarily complex, and I was just more kind of brought up, I guess, on F equals kx, so, but same thing. So what this refers to, there are several things going on here. Firstly, F is the force of the spring. And this can be this goes two ways. This can either be the force that you're applying to a spring or the force that a spring is applying to you. It doesn't really matter which it is because they're always the same. But yeah, F is the force of the spring. And we measure that in, let's just talk metric right now. Measure that in newtons. K is what we call this spring constant. And this is a measure of how stiff the spring is. Okay, and the correct word to use is stiff. Like you have stiff springs, you have soft springs. So the springs that are under your car in your suspension system, those are what I would call pretty stiff springs. What that means is they are very, very resistant to being flexed, to being changed. Okay, a soft spring would be like the one that's inside your ballpoint pen, like those little clicky ones that have a little spring on the pen barrel. Is that the right word? Or inside the barrel? Those you can squeeze with just like a little bit of a motion of your fingers, and they don't offer almost any resistance. So that's a soft spring. It doesn't matter if it's stiff or soft. We're always going to measure that in units of force per distance. So if we're talking metric, newtons per meter. I'll come back to that, but the X is the, let's see, what's the best way to describe it? Well, it's just it's the change in length. And that is absolutely why he used the delta. Okay. Why it was lowercase delta, I'm not really sure. But X is the change in length, and so that is measured in meters if you are in the metric system. So here is how we use this. We say to ourselves, and this is a diagram kind of similar to what's in the book. I'm just going to go horizontally. We have a particular spring, and this spring has a certain length. Let's say it is a 10 meter long spring, which would, by the way, be a really, really long spring. But that's okay, because anything can function as a spring. You could have a metal cable. You could actually use that as a spring, because everything has a spring in it, but don't worry too much about that. Now, this 10 meter long spring, then, you might walk up to that spring and then subject it to a kind of a tug of war. Okay, and you pull on it. Let's say you pull both ends, and you know, like any good physics tug of war, it's the exact same force on both ends. Let's say you have to apply 1,000 newtons of force to make this thing stretch out in the way that I'm drawing it right here. And let's say as you do that, it goes out to be 12 meters long. Okay, you just stretch this thing out. Okay, you see that? When the thing is given to you, it's 10 meters long and there's no force happening. And when you apply 1,000 newtons, it pulls out to be 12 meters long. Okay. So we can throw this into our spring formula, F equals Kx, or delta X, according to the book. The force that we applied was 1,000 newtons. The spring constant, we actually don't know that. That's K. That's what I guess we're going to find that out. The X is how much the spring's length changed. 2 meters. Okay, it went from 10 to 12. And by the way, this works just as well going the other way. If you compress a spring down to make it shorter, a lot of springs, that's the way they're designed to work, it still would be the same number. You would still write 2. If it went from like 10 down to 8, you'd just write 2. Interestingly, we don't typically need to worry about positives and negatives with spring situations, at least very simple ones, because it's just obvious what's happening. There's not much need for sign convention. So we'll keep it like that for our lesson. Now we do the math here. 1,000 divided by 2 on both sides would give us 500. Okay, so there you go. Just to restate it with units, the spring constant for this particular spring, this one right here in front of us, not all springs, just this one, is 500 newtons per meter. And these units are actually telling us something very significant, this newtons per meter, this force per distance idea. This is telling us that if a spring has a stiffness of 500 newtons per meter, what that means is that it takes 500 newtons for every 1 meter that you want to stretch this spring by. 500 newtons per every meter that you're going to stretch it by. Okay, so you might have, as I said, you might have a very like a relatively gentle kind of spring. Maybe you have a spring constant of 10 newtons per meter. Okay, different spring. Okay, I'm saying this is for like a little one, a simple one, but a different one. If you have a 10 newton per meter spring, that means it only takes 10 newtons to stretch it by a meter. Okay, that would be a very, very soft spring indeed. You might have a spring constant of 5,000. Let's switch out a metric here. Pounds per inch. Okay, that it would take 5,000 pounds to change the length of a spring by only 1 inch. That's a pretty strong spring. That might be like the ones underneath your car. Okay, so I mentioned the spring thing because it's there in the book. It's a very, very common, very important physics principle. I don't think we're going to use it a lot, and if we do, I'll kind of reteach it a little bit at that point. But yeah, it just happens so much. Part of the reason it happens so much is because, like I said, a steel cable can be thought of as a spring. Every rigid, hard physical object has a springiness associated with it. Okay, everything kind of vibrates. Everything, if you press on it with force, will deform in some way. There's really not like a magical class of things called springs and then other things which aren't springy. Everything is really a spring, but sometimes it's just more noticeable. So that's why we have a little separate word on it right here. Okay, let me keep on going. I want to talk about the weight of objects. Okay, the self-weight of objects, if you like. We have absolutely already been referring to things with weight. In fact, even on the first screen of this week, I had a table, and I said, I just told you, I said, this thing has a weight of 80 pounds. Okay, so we've already been doing it, but I want to get a little more into what's going on there. So here's the formula to put in your notes, and of course you're taking notes, right? Because that's what you do. We have W equals mg, and I love what I saw in the book, that over the W and over the G was a vector symbol, but not over the M. Okay, so this is an example of a physics formula where we have a vector quantity arising from a scalar times a vector. Okay, and scalars times vectors, those are very, very simple situations. To some of you, I've been getting into the complexities of dot products, cross products for vectors times vectors. This is far easier than that. It just does exactly what you think. A scalar just makes a vector bigger or smaller just through simple multiplication. But these kind of formulas are pretty common. So you know that the m is a scalar because there's no vector sign above it. So let's do this in metric units firstly. G guess I could do the vector symbol. G is the acceleration due to gravity that all falling objects experience. In metric, it is 9.8 meters per second squared. I know that middle school students learned this with Mr. Alka, so I know that all of you have seen this. So this is the rate at which objects want to accelerate as they fall, if they could have it their way, if they could have their druthers. What a great word. M is the mass of objects. Now that could be different for any object. It's always going to be measured in kilograms, but it could be anything. Unlike that G vector, that is always going to be 9.8 meters per second squared. That's what we call a constant. Okay, that's like a fixed thing in the formula. We actually like constants. They make life pretty easy. And then W, of course, is that weight. If you're wondering why I'm coughing, it's because this is the second time I recorded this video back to back, because the first time I thought it was working and then it wasn't. So I'm getting a little dry throated trying to teach this dude twice. I hope you enjoy it. Okay, now I will also say, although 9.8 is a more accurate acceleration, for back of the envelope calculations, we will often just say 10, because 10 is such a lovely metric-ish number that it's just too good not to use, and it doesn't really affect the outcome in a huge way for most sakes and purposes. If anything, you'll get a slightly overestimated weight, which is always fine in engineering most of the time. Most of the time it's fine. So here's what we do with this. We have a one of our ubiquitous boxes. Stop auto-correcting me. Oh, that really wants to. And we say this box has a mass of 50 kilograms. And all you do is you run it through that W equals mg formula. You say, all right, what is 50 times g times 9.8? Yeah, I can write it out for you. W equals mg, 50 times 9.8, and I believe from memory that is 49 newtons. Okay. Now, although you couldn't show the mass as a vector, that's a property of the object. You can show, and you should show, the weight vector. Okay, the mass is the thing that describes the object, and it doesn't change ever. Like this object has a mass of 50 kilograms. That has to do with the amount of like molecules and atoms and molecular stuff that makes up that box in this case. The 49 newtons, that is actually location specific. It's location dependent. That 49 newtons will actually be a little less if you go up on top of Mount Everest. It might be like 48.9. If you go to the moon, it's going to be about 1/6 of that, which, gee, don't even try that. What is that, like 8? Boy, 9? I don't know. Something like that. But yeah, like that's the force of the planet pulling it towards itself. So greatly dependent on where you are, what's happening, what planet are you on. The good news is that since we're almost always near sea level on planet Earth, that's why we can pretty confidently say 9.8, or to make it even more rough, 10. Now, let's see. Let me put in green. I just want to do the same problem again using US customary units, because the US customary units are 39 feet per 32.2 feet per second squared. Or if you only want two significant figures, 32 feet per second squared. If you're going to use US customary, then technically you're supposed to use slugs for mass. But I will tell you this, I have yet to find an American who knows what a slug is. Okay? Like, you have to be a physics teacher basically, or even more so an engineering teacher. I've just never run into anybody yet, I think, who actually knew what a slug was, much less can have a good feel for, like, how much is one slug anyway? Is it big? Is it small? It's actually kind of big. Weight is the pounds, sometimes called pounds force. So, again, we might usually when you're in US customary, you actually start by knowing the weight and you go backwards to work out what the mass is. Okay, this is an interesting, freakish feature of working in metric or US customary. In metric, we typically start by knowing a mass because we put it on a scale and we get told how many kilograms or grams. In US customary, we typically read off a scale in pounds. So it's kind of strange. We actually hear mass if we are in Australia or England or India or Brazil or any of the 200-ish other countries that use metric. And if we stand on a pair of scales in the United States, and I think there's one other country, maybe Burma or somewhere, Myanmar, we actually are reading off the force of gravity. Now, the truer thing, by the way, is that the American system is more correct there, because you are truly reading off the force of the spring that's inside the scale. Mass can only be inferred from that. Anyway, I'm getting way deeper than I intended to. Let me go back to the problem. We would say weight equals mg. Let's say that our object in front of us, has like 150 pounds of weight. We don't know what the mass is, but we do know that acceleration due to gravity is 32.2 feet per second squared. So in this case, we would have to do some division with some odd numbers, and we would find we have 4.7 slugs. Okay. That is gained from 150 divided by 32.2, 4.7 slugs. Okay, so Mr. Meath, I weigh a bit more than 150 pounds. I'm about 157 these days, and I'm going to say I was about 155 before coronavirus. So, I have a mass of about 4.7 slugs. And I don't know how I feel about that, because I don't really have a sense of how big or small a slug is. Is that good? Is that bad? That's just what it is. You'll very, very rarely see it. So conveniently, you're typically talking straight away in terms of force in US. And then if you're in metric, you do kind of have to do all this sort of stuff here, where you convert between the two. All right. Okay. I think we'll go to our last topic for today, and that is mass and density. This might be a fairly simple topic, especially if you have done chemistry of any sort at any level. So mass and density relate very closely to what we were just talking about, okay, like that weight and mass and everything. But I just want to show you, and this was also in the book, it was just like half a page, but I wanted to show you how we get masses out of knowing the properties of an object. So the formula that was given was that mass equals rho capital V. Let's dig into that. So M is mass, just like we know, measured in kilograms. let's say this here. M is mass, measured in kilograms. Rho, here's another Greek letter for you. Add this to your compendium of Greek knowledge. We say it R-H-O, rho. Rho is this is the lowercase version. It's the letter R in Greek. And for whatever reason, rho is the symbol which has become popular usage for density. Okay, density is, you know, how much stuff there is in a particular object for the amount of space it takes up. And you can see that reflected in the units, kilograms per meters cubed. Okay, how much mass per volume. The units always give you the clue to what's happening. When you draw rho, by the way, it's a little bit like drawing, here let's practice a few of these. It's a little bit like drawing like a slanted P, and you don't give it any like little serifs or tails or anything like that. So when I draw a P, I would do a P like this, so I make a point having like a little thing right there. But when I draw a rho, it's kind of a slanted one, and I don't show anything up top. If you do show that little tag up the top, that thing right there, then it just looks like the letter P. We don't want that. Now V is volume. Capital V, I'd say, is most likely to be used for volume. Lower V for velocity. And this is measured in meters cubed. Now I think it should be pretty obvious, you even like see it right there in the list of units, that all those units balance out across the formula. When you take your kilograms per meters cubed and you multiply them by meters cubed, you get cancellation happening and you get kilograms, which gives you the mass. Okay, before I go any further, let me give you the the equivalent units in US customary. And I'm a little torn here because if I'm going to be strict about this, if we're talking mass, well, gee, I have to say slugs, and slugs per cubic feet and cubic feet. I'm fine with the cubic feet. I'm feeling kind of awkward about the slugs. I have never, ever yet once seen a density for an object listed in slugs per cubic feet or slugs per cubic inches or anything like that. Here's what you do see. You see mass listed in pounds. You see density listed in pounds per cubic feet. This is the practical version. This is the one that people actually use. This is the, I don't know, correct but questionable, impractical version. So this is, as I say, this is a little awkward, a little embarrassing. We're talking about mass, but we're using pounds. And pardon me if I don't know if you can hear those crows outside. I can. I guess what we're saying is we're converting the slugs into pounds. We're kind of, yeah, we're saying pound mass. I don't know. It's a little confusing, but Americans just don't tend to think in terms of mass, unfortunately. They tend to think in terms of force, whereas metric people tend to think in terms of both. Part of this is because all physicists everywhere around the whole world, even in the United States, physicists only do physics anymore in metric. Nobody does physics in pounds and feet and seconds. We do it in meters, kilograms, and seconds. And you only really need to worry about mass when you're worrying about physics, about like inertia and how things accelerate and move. When you're dealing with like buildings and roads and bridges and stuff that doesn't move, statics problems, then you're really more worried about forces than masses. That's why pounds is the language, even though technically it's a force, it's not a mass. So again, I'm sorry I'm getting way deeper than I thought I would, but I'm trying to give you the backstory here and tell you why it is so. that we would be using force per volume when I'm clearly telling you mass per volume. Anyway, back to it. Okay, the most useful thing I think here is to give you a sense of just what kind of scale it is we're talking about. So this is a cube of water. Okay, water doesn't typically come in cubes. I'm not talking about frozen water. I'm saying this is a cube of water, 1 meter by 1 meter. Let's see, by 1 meter. If you have a 1 meter cube of water, it has a mass of exactly 1,000 kilograms. If it's fresh water, by the way. If it's salt water, it's a little heavier, a little more massive. So think of water as being the standard when it comes to these things. Because everyone knows how much water weighs, how much it feels like when you pick it up, when you drink it, when it hits you in the ocean, all that kind of stuff. Water is universal, so water is kind of like the standard. When you have things like wood, okay, wood is a very common thing to have to calculate. Oh, gee, to have to calculate masses and densities of. Wood can vary a lot. Wood can have a density. There you go. Density of wood, density subscript wood, can be anywhere from like 300 to 900 kilograms per cubic meter. So what that means is, compare that to water. Wood is generally like a third to almost the same as the density of water, which is why wood floats. Almost all wood floats. There are a couple of species of wood that are slightly more dense, but generally wood floats. What else do we have? We have steel. Okay. Steel is obviously very, very, very common in engineering. We build a lot of things out of steel. I did write Fe, by the way, which is the chemical symbol for iron, because steel is mostly iron with carbon as the primary additive. You add carbon to steel, you add carbon to iron, it becomes steel. That's why steel has been able to be made since, I think, the Middle Ages without too much difficulty. You can make it without a lot of technology. You can't make very good steel, but you can make steel. Steel tends to be about 7,900 kilograms per cubic meter. So that, in other words, about 7 times, closer to 8 times the density of water, which is why steel sinks. By the way, the only time that steel doesn't sink is if you get a steel needle and you can put it very carefully on the surface of water and it will stay there because of surface tension. Not because it is less dense than water, but just because it clings to that surface tension. Special case. Let's see, I'll use brown. No, I'll use gray again. So now think of concrete. Okay, this is concrete. This is what it looks like. Okay, trust me. You can see all the aggregates, all the stuff inside of it. Aggregate is what we call all the stones and bits and pieces that actually make up a lot of concrete that's bound together. Concrete usually has a density of about 2,400 kilograms per cubic meter. In other words, about 2.5 times more massive than water for the same volume. And again, that's a very, very common thing to use, a very common material to use, that is, when you're building things, stuff. And one more, if we want to go to the extreme end of the scale, if you can get really, really dense plutonium. Yeah, let's say this is like a rod of, oh, wow. A rod of like enriched radioactive plutonium. That can be somewhere around the 20,000 kilogram per cubic meter mark. 20 times as heavy as water. That's hard to even imagine, that you would pick up a lump of something and that it's about 20 times heavier than its wet equivalent. Because water feels pretty heavy as it is, but there are things out there, things like gold, silver, platinum, palladium, uranium. They're all very, very dense metals. Okay. Now, when it comes then to calculating the weight of these kinds of things and the mass and the volume, all that, this is the interplay here. What you really need to do is just use some basic geometry. So look, here's our concrete block. Let's say this concrete block is like 2 meters tall, 5 meters in the other direction, and 3 meters in the other direction, and it's a cube. So you know that volume of cubes is like length times width times height. So you throw all those things together and you get 30 cubic meters. Then you go to your mass formula. Mass is rho times V, and you say, oh yeah, so this is about 2,400 times the 30. 24, 48, what is that, 52? Nope, 72, sorry. Kilograms. And that's how you connect this idea of like how dense is something, what is its volume, what is its mass. Okay, it's all interrelated. And then from there, going back to our previous slide, you could also work out what is that weight force. And you take that 7,200, you multiply it by the 9.8, and you get the results, which I will do right now on my calculator. 70,560. 70,000, I'm going to round up, and that is in newtons. Okay, I kept it to 3 significant figures because all of my data within my calculations really was never more than 2. So as it is, I'm being kind of generous. Okay, so that is how you connect mass, density, and volume. That is how you connect weight and mass. And then we also talked about springs, how you can calculate those simple spring forces, although as I said, you're not really going to see a lot of that come up in the work that we do. But if it does, we'll look at it again. Okay. Thank you for listening well. We are coming up very close to 55 minutes today, and I do apologize for getting a little deep into the weeds when it came to all this talk about slugs and pounds. It does get kind of confusing. Unfortunately, it's kind of a problem which is better just left ignored and not worried about, because it doesn't come up in practical habit. So get out there, do your engineering. Let me know if you have any questions, and I'll be in contact very soon about some good, exciting developments on the furniture project. I'm going to define that more clearly. I've been talking to actual people who want actual things from you, and so we'll turn our brainstorming into something solid very soon. All right, see you later.